Okay, well, let's finish up the example we were doing last time. So we were doing this example. We have a vertical wall, and there's a pin and slot joint at the bottom like that, and 100 Newton force applied there. The masses were each 1 kilogram, and the lengths of each of those members was 1/2 meter. And at this instant, it's starting at rest. Okay, and then this we called member 1, member 2, joints A, B, and C. And we want to calculate the acceleration vector of C. And I'm going to list out the equations we have so far. Let's think about, so if you see a problem like this, how many equations are you going to get from the rigid body analysis, from doing the rigid body analysis of those members? How many? Well, let's do it one by one. So member 1 has a fixed point. So how many equations are you going to get from Newton's laws for that member? Yep, just one, yep. There's no Newton's second law, so you're just going to get the rotational equation. And then member 2 doesn't have a fixed point. How many equations are you going to get from that? 3, yep, rotational equation, and then 2 components of Newton's second law. So from the rigid body analysis, we have 4 equations. Okay, now let's think about the joints that need constraints. This one doesn't. We're just assuming that that's fixed, and so that's the end of it. But these 2 aren't fixed, so we need constraints at these 2. How many constraint equations are we going to get at that one? Yep, 2. Yep, the 2 components of the acceleration. And how many are we going to get at that one? Just 1. The one saying the x component of that acceleration is equal to 0. So we have 4 Newton's laws equations, 3 constraint equations. Okay, so 7 total equations. And so that tells us how many variables are we going to have in this problem? 7. We have to have 7 and 7 to solve it. So we're looking for 7 total equations. So far we've done 5 of them. Let me write those down. So we had 0.492 F12x plus 0.087 F12y minus 0.083 repeating alpha 1 is equal to 49.67. Equation 2 says negative F12x plus RC minus A2x is equal to 0. Equation 3 says negative F12y minus A2y is equal to 9.81. Equation 4 says 0.246 F12y minus 0.043 F12y plus 0.246 RC minus 0.0208 alpha 2 is equal to 0. And then the last one that we've already found is the constraint equation for the pin and slot. So we're going to calculate the acceleration vector of the point C, and then we set the x component equal to 0. And that's the fifth constraint, or the fifth equation, 0.246 alpha 2 plus A2x is equal to 0. Okay, so the only thing we have left is the constraint equation at B. This is the most important type of constraint to get used to because this is the one that occurs in every single linkage problem you're going to do. So take a few minutes, and these angles are 10 degrees. So now we're doing the constraint at B. And I guess let's do this way. So let's first calculate the acceleration at B according to member 1. I'll give you a little time to do that, and I'll do it. And then after I do member 1, I'll give you a little time to do member 2. So for now, just start out by calculating the acceleration of that point B according to member 1. So this one has a fixed point. We're talking about this top member. And so that acceleration is just going to be circular motion. So the acceleration at B is equal to alpha cross R plus omega cross quantity omega cross R. Alpha is 0, 0, alpha 1. This all goes away because omega is 0. And then R is the vector that goes from the center of the circular motion to the point that you're calculating. So that's a vector that goes from A to B. Okay, so that's going to be 0.5 times, so 0.5 times the cosine of 280. Sine of 280. And so you get 0.087 negative 0.492 and then 0. So the acceleration at B, according to member 1, is 0, 0, alpha 1 crossed with 0.087 negative 0.492 0. And so you get 0.492 alpha 1 for the x component. And then for the y component, 0.087 alpha 1. And then 0 for z. Anybody have any questions about that one? And then go to member 2 and do the same thing. This one doesn't have a fixed point, so you're going to have to use relative motion. So take a few minutes and do that one. So for this one, we're going to have to calculate the acceleration of b relative to the ground using relative motion. So this is equal to the acceleration of b relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. This is a variable we've already defined. This is A2. And this is circular motion. So the acceleration of b relative to the center of mass of 2 is alpha cross r plus the omega stuff that in this case is all 0. Alpha is 0, 0, alpha 2. And r, so r is the vector that goes from the center of the circular motion to the point we want. So that's from the center of mass of 2 to the point B. And so that is 0.043 for x and positive 0.246 for y. And so the acceleration of b relative to the center of mass of 2 is 0, 0, alpha 2 crossed with 0.043, 0.246, 0. And that is minus 0.246 alpha 2 for the x component and positive 0.043 alpha 2 for the y component. Well, now we have to use relative motion, so the acceleration of b according to member 2 is negative 0.246 alpha 2 plus a2x. We're just adding on now the acceleration of the center of mass. And then 0.043 alpha 2 plus a2y. And now finally, the constraint is just setting those two equal. So equation 6 says 0.492 alpha 1. I'm going to move this stuff over to the other side of the equation. So plus 0.246 alpha 2 minus a2x is equal to 0. Everyone following what I'm doing there? I just set the two equal and then I put it in the form that we're used to for reduced row echelon form. And then equation 7 says 0.087 alpha 1 and then subtract this stuff. Minus 0.043 alpha 2 minus a2y is equal to 0. And now we have our 7 equations for 7 variables. So take a couple minutes now and put this into reduced row echelon, put it into the matrix, do reduced row echelon form. Here's what I got. I got F12 is equal to 48.7. I'll just go to the 10th, 26.7. And then our C, I got negative 20.32. And then alpha 1, I got negative 280.6. Alpha 2, I got positive 280.6. And then the acceleration of the center of mass of 2, I got negative 69.0, negative 36.5. Cale, can you tell me what you got again for F12?
Yeah, I got 27.8 and 40.
Okay. And then for alpha 1, you got negative what?
389.1.
389. And for alpha 2, you got the positive of that. Okay. And anybody else have answers? All right, well, let's just, let's go with Cale's. Who knows? By the way, what are some ways you could, so this is just a class, we're just making up problems and getting practice doing them. It's not real urgent that you get these right, but it's not very hard to imagine engineering scenarios where you really have to know your answers are right. So the first thing you do for that is that instead of doing it by hand, you write programs to do this stuff, and then you check your programs before you use it for the important stuff. You check it on other stuff, But if you're doing a problem like this by hand and you need to get the right answer, what are some things we could do to check these answers? Yep.
You could enter all of your numbers twice.
Yeah, so, right. So one thing you could do is just let that sit for a second and then do the problem again and see if you get the same thing, Another thing you could do is take these answers and plug them back into all your equations and see what equations hold, So take your forces and your angular accelerations and just check them in each one of these. Make sure that those come out. If you entered something in the wrong place in the matrix, one or more of these equations are not going to work out. Okay. So it's always good to know, to have some strategies for when you really want this stuff to be right. Okay, well, I didn't ask you for these 7 variables. I asked for the acceleration of that point C. Okay, so how are we going to come up with the acceleration of that point C? That point C is on the body 2, okay? And that body 2 doesn't have a fixed point. So we're going to plug that into our acceleration equation. So the acceleration of C relative to the ground is equal to the acceleration of c relative to the center of mass of 2 plus the acceleration of the center of mass of 2. This is just our A2. This is circular motion. I said I was going to use Kale's, but I'm not. I'm going to use mine because I have all the values right here. Okay, so the acceleration of c relative to the center of mass of 2 is alpha cross r plus, we know that those omegas are 0, so the alpha vector is 0, 0. This is alpha 2, so 280.6. The r vector is from the center of mass of body 2 to the point C. So that's going to be negative 0.043, negative 0.246. And I got 69.03, negative 12.07. Then we'll add that to the acceleration of the center of mass. We have 69.03, negative 12.07, plus the acceleration of 2, which is negative 69.0, negative 36.5. And you get 0 for x, basically, if you round it off, and then negative 48.6. And does that make sense with the joint constraint that we have there? Yeah, we required that it doesn't have any horizontal acceleration, and that's what we got within round-off error and stuff, you know. If you want to eliminate round-off error, just keep more decimal places. Any questions about that? Okay, I want to bring up two things that this question, this problem sort of raises. We have done examples of pin and slot joints and rollers and sliding things where the track of motion is along the x-axis or along the y-axis. Okay, what if so these aren't things that are going to come up on tests or anything like that, but it might have just sort of popped into your head. So two questions. First, what does the constraint look like when the path of a joint so like we're talking about the like the slot of a pin in a slot joint isn't along X or Y. So like, for example, what about if you have a member with a pin moving along a slot like this, that's in between X and Y. What would that joint constraint look like? Well, if it's, say, horizontal, you calculate the acceleration. If I call this C, you calculate the acceleration of that point C, and then you say, okay, it can move horizontally, but the vertical acceleration is 0. Okay? So how do you think that sort of generalizes to a slot that has part of the, that's at an angle like that?
Could you use a unit vector or rotated coordinate system?
Yes, I think the unit vector is the easiest way to do it, yeah. So find a unit vector that's perpendicular to the slot. I'll say to the path, more general than the slot. Okay, and then the dot product, so I'm going to call that U, okay? Then the dot product of U and the acceleration of C have to be equal to 0. Okay, is the dot product of two vectors a vector or a scalar? Scalar, and so this just gives you one equation just like it would if those were along X or Y. Are you with me on that? Anybody have any questions about that? And notice that this is exactly what we do. I mean, this, we didn't think of it this way, but this is exactly what we do with horizontal and vertical constraints. I mean, so in this case, a unit vector that's perpendicular to that path is 1, 0, right? And so what we did is we calculated the acceleration of the point, I guess we did it yesterday, but we calculated the acceleration of that point C, and then in essence, we took the dot product of that with the vector, unit vector 1, 0, and that gave us our constraint. Okay? Now the second question is, okay, I've done a lot of problems because these are long problems anyways. I've done a lot of stuff where we're saying it's starting from rest. There's no angular velocity at the instant we're looking at. And it's not too hard to imagine how you would put those angular velocities in there. But one question is, so like, in some cases, like if you had a floppy thing that was connected at A, but this pin and slot joint wasn't there, so the end C just flapped around, then those two angular velocities could be anything, You can assign those totally independently. But notice they're not independent here, okay? So, for example, you could see a problem like this where somebody just said, okay, the angular velocity of the angular velocity of body 1 is 20 radians per second positive, okay? And they didn't even tell you anything about body 2 because its angular velocity is constrained by the angular velocity of body 1. And so if you saw a problem like that, or think of it in like my case, like how would I go about coming up with angular velocities to give you that don't violate the constraints? Okay? And the answer is, okay, so when the body's angular velocities are not independent, how do you find one from the other one? And the answer is you approach it very similarly to how you approach constraints on the accelerations. So it's like the constraint equations. You would say something like the velocity at B is equal to omega cross R. Okay? The velocity at C relative to the ground is equal to the velocity, and I'm not going to use the center of mass now, I'm just going to use the joints here. The reason that we use the center of mass when we're doing accelerations is because the centers of mass come up in Newton's second law. So those variables arise naturally. We're not being told anything about what variables to use for the angular velocities, so I'm just going to use the joints. But the velocity of C relative to the ground is equal to the velocity of C relative to joint B plus the velocity of joint B relative to the ground. This is what we just calculated. This is circular motion about that point B. And then once you've come up with an expression there, what do we know about the velocity of that point C? Well, we know it has to move along the slot. So the velocity at C, X component, has to be equal to 0. And in this case, because those two things have the same length, we would get, you know, the result we would get is that angular velocity of body 2 is equal and opposite to the angular velocity of body 1.
Mm-hmm.
All right?
So is it an even ratio, so one's twice as big or one rate?
I don't know. That's a good question. Maybe calculate it and give a report to the class. Yeah. Okay, any other questions? All right, that's all.